Okay, well today the topic is finite state machines. And here on this first slide we have a definition of a finite state machine. It consists of, I guess, maybe 5 parts. Okay, so the first part of a finite state machine is we have a finite set of states, all right, that are called nodes, and they're represented by circles. And the second part is there are transitions between the states represented by directed arcs. And the third part is each arc is labeled by a terminal character. Now, what is a terminal character? In a grammar, what are the 4 parts of a grammar? What's the first part of the non-terminal what? Alphabet. Non-terminal alphabet. And what was the second part? Terminal alphabet. So these, and then the third one was set of rules of production, and the fourth one was what? A start symbol, which is an element of the what? Non-terminal. Okay, so these, each arc labeled by a terminal character, that corresponds to the terminal characters in a grammar. Okay, that's the same thing. Those are the characters that you actually see when you see a valid sentence in the language. And then in the same way that a grammar has a start symbol, a finite state machine has a start state. So they're kind of similar. And then we have a non-empty set of states that are designated final states. So this is the definition of a finite state machine in general. And here is an example of one in figure 7.11. So the states in this figure are labeled A, B, and C. So those are the nodes. And you can tell which one is the start state, obviously. Which one is it? A is the start state. And then you see that there is an arc from A to B labeled by what? Letter. So that, I didn't want to put down, A, B, C, D, E, F, G, so I just said letter. Okay. And digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So there's an arc, so there's an edge, a directed edge from A to B that's labeled letter, and then there's a directed edge from A to C that's labeled digit, and then B has a transition to itself on letter and digit, and C has a transition to itself on a letter and a digit. Okay? And now in a finite state machine, the way you designate what is called a final state is with the double circle. So how many final states do we have here? 1, and it is state B. All right? So this is an example of a finite state machine. Now, why is this finite state? What does this finite state machine do? Well, do you recall there are 3 ways to specify a language, the syntax of a language? What are those 3 ways? There are 3 ways to specify the syntax of a language. What are those 3 ways? There's a grammar, finite state machine, and regular expressions. And so the reason this is kind of similar to, like, has some of the elements in it that a grammar has is this is the second way to specify a language. And this particular finite state machine specifies the rules for constructing an identifier. And the way it works is this. Here's how it works. There are these, in this next slide, we have what are called parsing rules. And so, with the grammar, what we did is given a sequence of terminal characters, how does a grammar work? That sequence of characters is valid if you can do a what? With the grammar, how did that work? When we had a grammar, if you have a sequence, if you can do a what? Yeah, if you can do a derivation. So that's the way you determine with the grammar, the way you determine whether it was valid is if you can do a derivation starting with the start symbol and get that sequence of terminals, then that shows you that it's valid. Okay, so this finite state machine, it's the same question. The same question is a sequence of terminal characters valid? And so this next slide describes the parsing rules. This is how you use a finite state machine. So this corresponds to, like, trying to do a derivation to get a sequence of characters, to derive a sequence of characters. with a grammar, but now we're using finite state machine instead. So here's the rules. So what you do is you start at the start state, right? So that's the start state, and then what happens is you imagine you have a string of terminal characters, and you imagine you have a little cursor, like on your screen, that's in front of the first character, and what you do is you scan the string from left to right. And each time you go one character to the right, then on the finite state machine you make that transition from that state to the next state that's pointed to by that character. Okay? And you just keep doing that over and over and over again. And then after the last terminal gets scanned, if you are in a final state, then it is valid. And if you're not, then it's not. So that's how it works. So what I've done here now on the board is I've reproduced figure 7.11. And just graphically, here's how it works. So do you remember when we did a grammar for identifiers, and do you remember how we parsed CAB3, and that was a valid identifier using the rules of production with a grammar? Well, here's how you would do it with this finite state machine. What you do is you just imagine there's a little, here's a little car tooling down the freeway on this finite state machine, starting to start. And here what you do is you imagine that there's a cursor right here, boom, boom, right here at the beginning. All right? And what happens here, the way it works is you scan this. So now the cursor is here. Now what letter did we scan? A C. And because we are here, and C is a what? Letter. That means we do what? We go from here up to here. Now does everybody see how that worked? And then what happens is you scan the next letter. So whoop, and that one is another what? Letter. So here that's a letter. That takes us back to here. And then here and then here boop boop, we do what? Scan the B, that's another letter, so we go around here. And then what? 3, and 3 is a what? A digit, so we come down to here. And now we're at the end, and the question is, so now we're at the end, and the question is, what state are we in at the end? B, which is a final state. Conclusion CAB3 is a valid identifier. Does everybody see how that works? That's how finite state machines work. Okay? Now, yeah, question?
So in this terminal?
Well, yeah, that's a good question. Suppose instead of being CAB3, suppose this were like 23 skidoo. What would happen? You would start here, that you'd scan the 2, and what would happen? 23 SKADOO. You'd be done. And when you're done, where are you? In a state that is not a final state. That's called a final state. And a state that's not a final state. And therefore, 23 skidoo is what? Not a valid identifier. Now, does everybody see how that worked? Yeah.
Why does it even bother to have that whole second half then?
Well, because these are the rules. This is a complete finite state machine, and the rule is you make a transition, you keep making transitions, and in the end, if you're not in a final state, it doesn't accept it. Actually, you make a good point. What we're going to see now is we're going to see another way. We're going to see a simplified finite state machine. We're going to actually answer your objection. Did you have a question?
Yeah.
It was the same thing?
Yeah. It's like
Yeah.
with the letter, it's valid.
Well, yeah, but the question is, how does a finite state machine do that? And this is the way they work. What we're showing here is how finite state machines work.
So even if that,
Well, yeah, good question. Good question. So So what you're pointing out, and what is kind of obvious here, is what's the purpose? What is the purpose of state C in this finite state machine? It's just to collect. Once you get to state C, you know what? No matter what you have coming up, it's not going to be valid. So the question is, what's a more efficient way to do this? And a more efficient way to do this is by constructing what we call a, oh wait, before we go on, one more thing in figure 7.12. So in figure 7.12 what we have is a table representation of this finite state machine. Now this is really important. Look at how this table is constructed. What do we have on the column on the left? The column on the left, we have listed all of the what of the machine? The states. States A, B, and C. Are you with me? And we have indicated the start state with an arrow to A. And, you know, on the table, we just put one circle around the B to indicate that that's a final state. Are you with me? And now, do you see how the body of the table works? Where it says next state and then letter and digit. So what is it? What is this B here under letter? On the first row, what is that B under letter? What does that mean? That means that if you're in state A and you get a what? That means the next state will be what? B. Now, does everybody see how that table works? And if you're in state A and the next one is a digit, that's a C. Do you see that that corresponds? That's just a table representation of this. Because look, how are you going to store this in a computer? You know, if you're going to have a finite state machine, well, here we can do this with an array. See? But here, you know, you see what we're seeing? So does everybody see the correspondence between that table and this figure? All right. Now, as you pointed out, the only purpose of this state C is kind of like to collect the garbage. You know, if you ever get into this state, you're kind of like stuck there, and you know that it's not going to ever be valid. So the way we can improve this machine and make it more efficient is by constructing what is called a simplified finite state machine. Now with the simplified finite state machine, basically what we do in this example is we just get rid of this state right here. So what will happen is figure 7.13 shows what happens if we get rid of this state here. Are you with me? And so now we just have start, and that goes to A, and we have a transition from A on letter to B, and B is the final state, and we have transitions from B to itself on letter and digit, and we just don't have the other ones. All right? But now, if you're going to have a finite state machine like this, then the rules are different. The parsing rules are different. All right? So let's take a look at the simplified finite state machine about of how that works. So in a simplified finite state machine, not all states have transitions on all terminal symbols. Yeah? So now there's two ways to detect an illegal string. The way that we did it before, you may run out of input and not be in a final state. So in that case, it's not, you have proved that it's invalid. But on the other hand, you may be in some state and the next input character does not correspond to any of the transitions from that state. In that case, then you know it's invalid right away. So for example, let's modify this finite state machine to look like this. And now if we have that string CAB3, we still go CAB3, and boom, it's valid. But then if we have like 23 skidoo here, now what happens is we are in state A, we scan a what?
A digit.
A digit. And we're in this state, but there is no transition from this state on a digit. Therefore, we know right away that it's invalid. Now, does everybody see how that works? Now tell me this, riddle me this, Batman. What is the state transition table going to look like for a simplified finite state machine? Because here was the table for our, 7.12 was our table for a full finite state machine. And notice what does figure 7.12 have? For every what? For every current state and every what? In input, there is another state. So now what have we done to the table? Yeah, see here in figure 7.14? Now does everybody see how that changes the shape of the table? Because now if we are in state A and we have a digit, what do we have? a blank entry in the table. But now our parsing rules are different. There's two ways to fail instead of just one way to fail. Yeah, question?
Is there a general way to do this story in a computer?
Yeah, we're going to see. It's tricky. If you're going to use a table implementation, it's kind of tricky. You could have like a special symbol that is a fail symbol, and that's how you'd have to implement it. But for our purposes, we'll just keep it blank. Yeah, good question. Yeah, there's always how we implement these. Oh, by the way, the reason we're doing all of this work on finite state machines is because you are going to program finite state machines in order to do your translator. See, that's why we're doing this. So we're not going to use grammars, we're going to use finite state machines. So this is, so think about how, we need to think about how we're going to implement. We'll see tomorrow how to do implementation. Okay, now the next big concept is the concept of non-determinism. Okay, now here's what non-determinism is in a finite state machine. What happens is, like if you have a state here, call it state D, and you have like, you could have like a transition on A to here, some other state, a transition on B to another state, and you might have what? A transition also on A to a different state. Do you see? Look, what you might have is you might be in this state, and if you get an A, you say, well, you could either go here, or you could do what? Or you could go here. So you see here it says at least one state has more than one what? Transition on the same what? Character. Do you see what we're saying there? All right. So now what happens is, and what this means is that, if you start here in your car, here's your okay, and you're moving along, and you scan an A. Now, what's your dilemma? What is the dilemma? Which path? I've reached the fork in the road. That fork, take the one less trod. What was it? So how do you know which one? So you got to choose, right? So anyway, so you choose one. So you choose one. You keep going. But then what happens is, if you get to the last character and you are in a final state, well, you succeeded. So that proves then that the string is a valid whatever it is that you're looking for, right? But the thing of it is that if you wind up in a state and you finish scanning all the input characters, and you're not in a final state, have you proved that it's invalid? No, because what might have happened? You might have just taken the what? The wrong fork in the road previously. You see what I'm saying? So what do you have to do? You've got to back up, you've got to backtrack, and then keep trying all the possibilities. Only after you tried all the possibilities can you prove that it's not there, that it's not valid. Is everybody clear on that? So here, let's take a look at figure 7.15 for an example of a non-deterministic finite state machine. I don't think I'll take the time to draw that, but so let's just see if we can visualize a little car. So now let's do a parse. Let's do this. Let's try to parse plus D, D, D. All right, and let's just see if we can visualize on this figure what some of the possibilities are. So we start on the start state, right? And here's our little cursor. And what happens when we scan the plus? Where do we go? We go to B, right? Now, so we go to state B. And now when we scan this D, what happens if we're in state B and we have a digit? What could we do? We could stay at B, or we could do what? Go to C. Let's say we go to C. If we go to C, then what happens? When we scan this D, what happens? Oh, shoot, I don't have a transition from this state on a digit. So therefore, what do I conclude? Well, we can't conclude that it's not valid. We just have to do what? Back up and try another one. So now what should we do? We did plus to B, and then this D took us from where? B to C, and then this one failed. So now what should we do instead of that? We should go plus to what? B, and then what? This D to what? To state B, and then what? This D to what? State B, and then what? Then a digit to state C, and so there we have a successful one. So therefore it is valid. Now, does everybody see, can you visualize how that works? All right, it's really important to visualize, you know.
So, have no other options left?
Yeah, okay, that's a good question. The question is, does the computer brute force it? And here's, let me give you a nice fact from automata theory. When you take automata theory, you're going to learn that every non-deterministic finite state machine, you can prove that it's equivalent to a deterministic finite state machine, and there's actually a process by which you can transform it from a non-deterministic one to a deterministic one. So as it turns out, in practice, with the implementation, you don't backtrack, right? So a non-deterministic finite state machine, it's convenient for defining the sentence that you want to recognize. But typically what happens is you define it conveniently with non-determinism, and then you remove the non-determinism. So in practice, the machine doesn't backtrack. There's actually those of you who took, do you guys remember this? Those of you who are in programming paradigms? Remember when we did what was backtracking? What was the programming paradigm with backtracking?
Prolog?
That was Prolog. Remember, we actually did a non-deterministic finite state machine, and because backtracking is built into Prolog. But it was a slick example, but not too practical. Anyway. All right. So anyway, does everybody see this figure? Now, how could you do? How about DD? Is DD valid?
Yes.
And how could you do DD? A to B on a digit, and then B to C on the second digit. Right. So you can see that the plus and the minus are optional. All right. So everybody see that does it. That's the language of assigned. Oh, now what about the table? What about the state transition table? Because if we're in state A and we get a digit, where could we go? Either where or where? Either to B or C. So what's the table going to look like?
It's going to have multiple entries in each box.
It's going to have multiple entries in some of the boxes. Exactly. So here, does everybody see that in figure 7? Oh, and by the way, this is also simplified. So does everybody see that this figure 7.16 corresponds to that previous finite state machine? So if we're in state A and we get a plus, we go to state B. We get a hyphen, we go to state B. And we get a digit, and we can go to either where or where? B or C. All right? Is everybody clear on how that works? Correspondence between the table and the diagram, the graph. Okay, now next concept. In the same way that a grammar has an empty string, finite state machines can also have empty what? Transitions. Okay? So, and furthermore, what happens if you have the empty string concatenated with another string? That's the same as what? Just the other string, right? But now how does an empty transition work on a finite state machine? What happens in the finite state machine is, if you are at some point in your scan, like if your cursor is right here, and you're in some state, and that state has an empty transition from it, what you can do is, in the finite state machine, you can make the transition to the next state on the empty one, but what happens here? Look. Yeah, the little cursor stays there. You see what we're saying? So look, like here, if we're in state A, and we have the empty transition, and this to state B, and we got here somehow like this. Then what happens is, if we're in state A, and we're going to scan this next character, Well, if there's an empty transition, we can go whoosh from A to B, but this cursor stays right here. See, so without scanning. So what happens is an empty transition allows you to go from one state to another state without scanning a terminal character. All right? And by definition, any finite state machine with an empty transition is automatically classified as what kind? Non-deterministic. Okay? So that's because, you know, if you're in, because look, what if you had like a D here to some other state here? So do you see you would have a choice? You see, you would have a choice of either going on the empty one here or D to here. So that, because that gives you a choice, then that's considered, they're always considered non-deterministic. The state machines with empty transitions. So here's an example of that same machine that we had before for detecting a signed digit, a signed integer, only with an empty transition. So check this out in figure 7.17. So the start state is I, and we can either go, if we have a leading plus or a minus, we go to state what? F. But also we can go from state I to state F on what? On the empty transition. And then we can go from state F to state M on a digit, and then we go from state M to itself on a digit. Now do you see that this figure 7.17 is a really handy way to say that what? The plus, the leading plus and the leading minus are what? Optional. So see how convenient that is? So here, let's run through a few quick ones, a few short ones. So looking here again, I'm not going to redraw it with the little car, but in figure 7.17, suppose that we have this, plus D, D, D. Then, and we start at the start state, so then what would happen? We'd start here. The plus would take us to where? F. This D would take us to where? M. This D would keep us where? M. And this would keep us at M. So boom. So therefore this is valid. Right? But then what about this string? DD. So now we start here, and now what would we do in figure 7.17? Yeah, we'd take the empty transition to F, and then we wouldn't scan this. And then what would happen? We're in F, and what? And this D would take us to where? To M, and then this D would take us to M, and then we'd be finished with our scan, and we'd be in a final state, and so therefore this is valid. Now, is everybody, are we good with this? How this the mechanics of a finite state machine work? Question? Any? Good? All right. Oh, haha. And what about the table? What about the table now? Because now we have an extra what? Now we have an extra symbol. So basically, what do we have? Yeah, we have another, so now we're going to have transitions on plus, the transitions on minus, transition on digit, but then we're going to have an extra column for the transition on the empty transition. So does everybody see then that figure 7.18 corresponds to that finite state machine? Are we good? Okay. So if we're in state I and we get a plus, we go to state F. If we're in state I, we get a hyphen, we go to state F. If we're in state I and we have a digit, oh, there is no transition on a digit from state I. Then how can we ever get out of state I if we don't start with a plus or minus? We have the empty transition can take us to state F. Is everybody? Question? Any questions about this? Yeah.
So,
Yeah. We haven't talked about the concept of an inaccessible state, but let me. Actually, we'll do an example.
okay.
We'll do an example right now. So now here is the next concept, And you might have to, you might run into this in your project if you design, because one of the things you're going to have to do in your project is you're going to have to design a finite state machine. So this next topic shows how to remove empty transitions. Now let's see what this slide says. Given a transition from P to Q on the empty string. Okay, and it says given a transition from P to Q on the empty string. So let's let this state be P and this state be Q. And here, this is a transition. This is the empty transition. All right. And then it says what? For every transition from where to where? From Q to R. So now let's say that this Q goes to R. And this one is on what symbol? On A. All right. What does it say to do? Add a transition from P to R on A. So why would you do that? Let's suppose that you have some. Let's suppose that you have this. That you have like D E A G. All right. And let's suppose that you've scanned this, and here you are in your state P, and your cursor is right here. All right? Now, do you see then that how can we make progress here if this is the setup? What could we do? We could go on the empty transition from P to Q on the empty transition, and then after that we could do what? Go from and this cursor would not be advanced, and then we would go from where? From Q to R on what? On A. So then we could go from here to here by doing what? The empty from here, and then on A to here. Now, does everybody see that that's the way that could work if we had an empty transition? But look, you guys, if you can do this, if you can go from P to Q on the empty string, on the empty transition, and from Q to R on A, then with an equivalent machine, what could you do? You could just go from where? Yeah, you could just go from where? From P to R on what? On A, and then not even have this. Now, put that in your pipe and smoke it. Yeah, question?
So is that just an efficiency thing? Is that the reason you would want to eliminate that state?
Yeah, that's a good question, and the answer is yes. Because with the empty transition, it's non-deterministic. You'd have to try the empty transition and then not try the empty transition. So this is this is one of the steps in making a non-deterministic machine deterministic. Yeah. All right. So does everybody understand? So this pictorially is justification for this rule. Given a transition from P to Q on the empty transition, for every transition from Q to R on A, add a transition from P to R. And then with that what happens then is this, that takes care of this possibility. So then we can just delete this empty transition. Do you see what we're saying?
Do you delete state Q also?
Well, now comes the question that was raised earlier about an inaccessible state. Because what happens is, it's possible to draw a finite state machine with states that can never be reached. I mean, it's easy. Look, here, let's just do one. So let's just suppose that we have this state, and we can go to this state, and this state can go to this. We can transition from here to here. And then, suppose we can go from here to here, and from here to here, and from here to here. Okay? And suppose this is our finite state machine, and this is the final state. And this is the start state. Now, here's my question. Do you see an inaccessible state here? Which one is it? It's this one, right? Because look, starting at the start state, you can go from here to here, you can go from here to here to here, you can go from here to here to here, but you can never get from where? From the start state to what? To this one. So therefore, what can you do? Equivalently. Just do what? Just get rid of it. Gone. And that's an equivalent machine because you can never get there from the start state anyway. So it's just taking up unnecessary storage. But it'll never be accessed. So that's what an inaccessible state is. All right? Now, and so by removing this empty transition, that could make this Q an inaccessible state, in which case we could just erase it. Are you with me? Now there's one more rule. If Q is a final state, so here you know what we had before we eliminated this, we had the empty transition here. So here, if Q is a final state, you have to make P a final state also. So now why is that? See, if Q is a final state, and you eliminate the empty transition by inserting this one and deleting this, if this is a final state, when you eliminate this, what has to happen? This has to be a final state before you, and then you can eliminate it. See, because it's possible to get in the original machine, if it's possible to get to Q on the empty transition, and it's a final state, then P has to be a final state also. So that's another rule. So let's do a few examples. Here in figure 7.19, in part A of the figure, we see the start state is X, and then there is an empty transition from X to Y, and there's also a transition from X to Y on the terminal C, and then there's a transition from Y to Z on A, right? So now, do you see then how we got rid of that empty transition? What happens is we can go, because there's from the empty transition from X to Y, and then transition on A from Y to Z, that means we can insert a what? Transition from what? X to Z on A. Are you with me? So that's the equivalent finite state machine without an empty transition in part B. Does everybody see that? And here's that other one. Here's that other one from you know, that we had with the signed integers. So look, there is an empty transition from where to where in part A? From I to F, all right? But now there's also a transition from where to where? F to M on what? Digits. So what do? We erase the empty transition from I to F and make what? A transition from where to where? I to M on digit. Now, does everybody see how this works? Okay. Okay. Now here's one that another little bit more complicated one. So in figure 7.21, in part A we have the original finite state machine. Now what do we have? A transition from where to where on the empty? From W to X. But now from X we have from where to where? X to Y on A, and also from X to where? We have from X to Y on A, but also from X to where? X to Z on B. So if we get rid of the empty transition from W to X, we have to add not one transition, but what? Two of them. Does everybody see how that works? So that's where we have to transition from W to Y on A, and also a transition from W to Z on B. And that's how we get rid of that empty transition. But furthermore, because X was a final state, what has to happen? Yeah, W has to be a final state. Yeah. Is everybody following this all right? Are we good? Okay. So finite state machines. And actually, that's all I had for, that's it. Are there any now, I think last time we said that your homework was due tomorrow, right? We gave you a little extension. So this is the material that you need to do for your homework for tomorrow. That's now due tomorrow. Yeah, question? Yeah, because the way that so the question is in figure 7.21, why does W become a final state? The reason is because if you are in state W, see, look, suppose you are in state W. You are in this state, and you're at the end of your scan. Suppose you're in state W, and you're at the end of your scan, and X is a final state. So suppose it's like A, B, C, and suppose that you are right, and suppose that your cursor is right here, and you are at the end of your scan. Right? Suppose this is a small part of a larger machine. Okay, and you're here, and you're in state W. All right? And you're in state W. Well, look. W is not a final, with this empty transition, W is not a what? It's not a final state. But but what can you do with this empty transition? You can go from W to X and do what? Not do what? Not scan the next character. So that means with this empty transition, you have success. You end up in a final state, and therefore this would be valid. But if you're going to get rid of this, this still has to be valid for it to be an equivalent finite state machine, and therefore this has to also be a final state. Because when you eliminate that empty transition, you had the possibility to go there and stop. Does that make sense? So you had the ability to go there and stop and have the string be accepted. So if you're going to get rid of that state, you still have to, it has to accept the same, for it to be an equivalent machine, it has to accept the same strings. So if it's going to accept this string, then without that empty transition to the final state, it's got to be able to accept it in this state also. Yeah. That's a little tricky, but do you see the concept, you see the idea? Yeah, question? Yeah, good question. If you get to the final state before you're scanning the whole thing, you've got to keep on trucking. Yeah, you do.
So if you say get to a final state and there's nothing else, no way to transition out with the characters you ever named, would that be invalid then?
Yes, that's a good question. So if you are in a final state, you still have characters to scan, but there's no transition from that final state on any of those characters. The answer is it's invalid. That was a really good question. You see why? Because that happens. That can happen. That can happen. Yeah. So anyway, you're going to have some exercises to construct some finite state machines, and you need to think about this process of how it works, how it scans. Yeah.
The homework would be due in class or before?
Tomorrow. Oh, it's a written because of these drawings. Then I'm not having you hand them in electronically. So you can hand them in at 5.
Oh, okay.
Yeah. All right. Good deal. See you next time.